Okay, so let's look at some public key encryption. So in this part we'll look at some of the basics and see where public key is actually used. And then from there we'll look at the three main methods or methodologies that we could use, RSA, Elliptic Curve and ElGamal. Okay, so here is where public key is really used. Okay, so the main application that we have is this one here, and that's in the proof of identity. Okay, so with this we have a key pair, and Alice wants to prove her identity to Bob. So what she does is she takes some data and then takes her private key and then encrypts that data, or we would define that as a signing process. Then what she does is that she sends that data over to Bob. So it could be the hash of a message. So it's maybe an email that she's sending to Bob, and she's taken a hash of the email and then she encrypts the hash with her private key. So then Bob takes the signed data and then is able to get her public key in some way. She might send it to him. He might put that on his keyring, or he could get access to a digital certificate which contains the key. So that's where Trent comes in. Trent has created a certificate which Bob can use, and then Bob takes that public key off and then he decrypts the signature and checks it. Okay, so that is the main application of a public key. We can also use it within key exchange. So if we need to negotiate a key, a shared secret key, and we're going to use something like AES. So it's a good example is an SSL with HTTPS, where we're going to negotiate a key for the exchange. So what Alice does is that she has a key pair again, and then she'll take her private key and then encrypt the key that she wants to use, sends it over to Bob, and then Bob uses his Alice's public key to be able to sorry, wrong way around. Let me go back again. Okay. So what happens is that Bob will take Alice's public key. So Alice could be Google, say. So Google has a key pair that they use. So Google, or Alice in this case, sends over her public key to Bob. Bob creates a shared key and then encrypts it with Alice's public key. Bob then passes that back, and then Alice will use her private key to be able to decrypt the key that Bob has sent, and then they both have the same shared key. Okay, so it's equivalent to you accessing a website. So Google might pass their public key to you. You'll create a session key that you want to use. You'll send the session key back with Google's public key, and then Google will decrypt it with its private key, and then you'll be able to use the same shared key. Okay, the other method, the other application is that we could use public key to actually encrypt data. It hardly ever happens because of the processor performance issues, performance issues, but it's certainly possible for Alice to pass her public key, for Bob to encrypt some data and then send it back, and then Alice will be able to decrypt it with her private key. This doesn't really happen that much. Our two main use cases are this one and this one here. Okay, so I hope that makes sense. So the three fundamental methods that we have to be able to create a public key are integer factorization with prime numbers, discrete logarithms, and elliptic curve relationships. So what we need to do is to make a task for a computer that is so difficult that it's going to take too long for it to be able to crack it. So these are currently the three main methods that are quite difficult, are extremely difficult for computers to crack. Okay, but this one is the factorization of two prime numbers. Here. With this one, it's the inability to find x, even though we know g and p and y, it's really difficult for us to find that value of x. That's discrete logarithms. And the last one is what's called elliptic curve relationships, and we'll have a look at that. To give you an idea, elliptic curve seems to be taking over the world just now in its application. It's used in smart cards, IoT, Tor, Bitcoin, and so on. And our traditional method of using prime numbers is becoming more and more difficult to use. But with quantum computers, then these methods could be in trouble. Okay, this shows quite a light-hearted analysis of the strengths of the keys. So this one here is our symmetric key encryption equivalent. It's like AES. This one here is elliptic curve, and then this one here is RSA. And this is the amount of water to boil, the amount of energy it would take to crack each of these crypto standards. So it takes a teaspoon, the energy to boil a teaspoon for 35 bits. Okay, so it's obviously not very secure. For elliptic curve 70 and 242-bit RSA, you only need the energy for a teaspoon of water to boil to be able to crack those ones. Then as we go up, here we are here. Okay, so this is range security. This is 80-bit symmetric, 160 for elliptic curve, and about 1200 or so for RSA. Okay, so you can see that we need much smaller keys than we need for RSA. And then we would need all of the energy to boil all of the seas in the world to crack 210-bit elliptic curve and nearly 2000-bit RSA. And then these ones here are obviously extremely difficult to crack. So we're looking at 4K keys now to be able to keep RSA strong. Okay, so let's initially look at the RSA method and how it works. Okay, so the difficulty of it is that we take two prime numbers and we multiply them together, P and Q. And if the numbers are large enough, then it's actually extremely difficult to factorize them back into P and Q. If we can, then the RSA method is cracked. Okay, so there's the value that we get for n is much larger. It was twice the size roughly of P and Q values that we have. Okay, it was created by Ron Rivest, Adi Shamir and Len Alderman, who created the RSA method, and is the first real application of public key encryption. So with public key, what we have is a private key and a public key, and we can use them interchangeably. We can encrypt with one, but it's the other one that we decrypt with. Okay, so here is the method here. Okay, so we take two prime numbers. So in this case, we'll take P equal to 3 and Q equal to 11. So we get a value of n equal to 33. And then what we've got to do is we've got to calculate a value of phi. So phi is equal to P minus 1 times Q minus 1. So in this case, that's 10 times 2, which is 20. And then we've got to make sure that the value of E does not share any common factors with phi. Okay, so we define that formally as the GCD is equal to 1 of phi and E. So the factors of 20 are 2, obviously 4, 6 and so on, 5 and so on. Okay, so we can pick 2, 4, 5, 6 and so on, and 10 there. So let's pick a value equal to 3, because that doesn't share a common factor with 20. So our encryption key is now the E value and the N value. So we'd tell the world what those values were. So if someone wanted to encrypt something for us, they would use 3 and 33. Now we must get this to be correct, where D, our decryption key, times E, and then mod of phi is equal to 1. Okay, so there's code that allows us to do this, but we'll do it just manually. So we'll try 1 times 3 mod 20. That doesn't work. 2, 3, 4, 5, 6 gives us 18. Mod 20 gives us 18. And then if we try 7 times 3 is 21. Mod 20 is equal to 1. So our decryption key becomes 7, or one of our decryption keys can be 7. So our decryption key, or our private key, is now 7, 33. After this, so this is our 2 keys here, we then use an exponential cipher. So the cipher is equal to the message to the power of E mod n. Okay, so if we use a value of 5, that's 5 to the power of 3 mod 33, and that gives us 26. And then to decipher, we take the cipher, we raise it to the power of D, and then take mod of n, and then that should work there. So let's have a look here. Okay, so we'll generate a value of P and Q here. So in this case our N value is this. There's the phi, and there's our encryption key. We then calculate an E value and then a D. Then there's our public key and our private key. And then if we go through and cipher a message, this is what we get. So we get the result coming back again. And we have some examples here. Okay, so this is a real life example. Generate some keys. So the E, and there's the N. The N is the multiplication of our 2 prime numbers. The D value is always much larger. This is a common value of E that's used here. And we see the N, there's the encrypted value, and then we get the value back there again. Okay, so that's what our keys kind of look like. We've got much bigger value of D there. We normally pick a value of E, which is that value there, and then that's the N, which is our 2 prime numbers. Okay, so let's now look at elliptic curve, which is taking off massively and replacing RSA in many applications. So with elliptic curve, what we have is an equation such as this, and it produces an elliptic curve such as that. So the way that we implement this is that this has the advantage that if we draw a straight line, then a value P, so a value G here, and a value P, we will always be able to cut the curve at least 2 points. And the point we're interested in, this point here. So what we do is that we pick a curve. This is a common curve that's used now. It's called curve 55219. And we create a generator point, an XY point. And then we create a random number, and the random number is the gradient. We then project that to find the value p. So p is equal to n times g, just like the gradient here. That's our random number n. So n becomes our private key, g is known, and p is our public key. Okay, so we use this in Bitcoin, IoT, and Tor to be able to create our public and private key. Okay, so that's it plotted there. Okay, so this is curve 25519. It's used in a lot of applications. Okay, so it's used in Bitcoin generation. So in Bitcoin generation, we create our initial key, our private key. Okay, and then what we do is we convert that into a storable format. It uses base 58. From here, we create our elliptic curve public key. So it's a 512-bit public key, and then this will be used to create our address. Okay, so we've got this, we use a G value here. We create our private key, which is obviously this, and that becomes the gradient. And then from this we can derive the public key. That's then used to create a public key hash, and then we expose our address to be used for someone to send transactions to us. Okay, so here's a very basic outline of a Bitcoin transaction. So Bob wants to send Alice 10 Bitcoins. So she has a private key, she creates her public key, and then a public key address from that. Bob takes her public key address and then creates a transaction, and Bob will then sign with his private key for that transaction, and then that goes on to the blockchain. Okay, so what does elliptic curve actually look like, and how do we generate it? So in this case we're using OpenSSL, and we're using this standard elliptic curve, and what we're going to do is we're going to generate our private key. So hopefully this will create a nice random number for us. Okay, so in base64 that's what our key looks like, and it's also stored the parameters in there so that so that we can read it back in. Okay, then from here what we'll do is we'll use OpenSSL to take the private key and then to create our output, which is our public key. So this value here is the XY coordinate, is the random value, and here we create an XY point for the public key. And if we want to have a look at the parameters that we've actually used, we can then look at that with OpenSSL. Okay, so the prime number we've used, this one here. The generator we've used is here, and this is the order of the curve that we've defined. Okay, so you can have a look at some examples, but OpenSSL will give you some of the details and create keys for you. It's also used in the Tor network. So with the Tor network, what we do is that we create a key for each node, And then in this case, Bob will encrypt with each of the keys to go to Alice. The first key he encrypts is this one, then that one, then that one, and it creates an onion effect. When he gets to this node will decrypt with its key, the only key it knows, so we end up with this. As we go here, then it will decrypt this key here, so we end up with that, and then when we get to what's called the exit node, then the exit node will take that key off, and we end up with the data. So the way it works is to use this curve that we saw before, but we get a key negotiation, which is using elliptic curve. So initially when we're setting up the root, each of the hosts will negotiate with Bob on the key that they must use, and each one will use the elliptic curve Diffie-Hellman to negotiate what that secret key is. Okay, if you're interested, this is the main methodology that we use. We'll be covering the Diffie-Hellman method in another unit, but this is the basics of how the elliptic curve Diffie-Hellman method actually works for the key exchange. At the end of it, Bob and Alice will have this key that each of the nodes will actually use. And finally, we'll look at ElGamal. So ElGamal is to do with discrete logarithms. So with discrete logarithms, it's actually very difficult to find the value that has been used, even though we know G and P and Y. Okay, so we'll go into it in a little bit more detail, but the value of G is selected from what's called a cyclic group. So we'll explain this in a little bit more detail within key handshaking, but if I select a certain prime number, 59, there are only certain values that we can actually use for that. And it's to do with making sure that for every value of x up to the value of p that we use, we'll get a cycle, or we'll get a different value output. And we can see here that it hasn't worked because it gives us the same value for 1 and for 6. Okay, so we can use Python to be able to give us the values that we can use in there. So for 59 we couldn't use 5, for example. In this case, P is a prime number that we use, and if you're interested, then this is an example here of encrypting with ElGamal. And we can pick here, and hopefully we should get the same result here as in there. Okay, so that's been an outline of some public key. We went over RSA, which was use prime numbers, elliptic curve, which uses elliptic curve methods, and ElGamal, which uses discrete logarithms. Okay, thank you.